Okay, so this is a short video commentary about the solutions to the second lab in operational research and Monte Carlo simulations. And the goal of this exercise is just to remind you about Python syntax that is kind of required for linear programming and Monte Carlo simulations. And I have some resources on the PDF which are available from the DLE, Jason Raphael's notes which he did last semester. This web page here I have collect together some resources and some LinkedIn videos I've curated, which we have access to at the university. And there's some very good video introductions to Python, which can help you remind you Python or help build up your expertise in Python. So the first problem is just solving linear equations using Python. So as usual with Python, you use a kind of library to do this. So because we're doing linear programming, at least some of the methods, very small linear programming methods, you need to be able to solve a matrix equation such as this: matrix times vector equals a vector. So I gave you a hint for doing this, but if you look at Spider, let's look at the solutions. So as with many things in Python programming, often there's a library to do it, to do the calculation. So here we have, and then the key thing is representing this matrix equation in terms of kind of data structures in Python. So we're going to use the NumPy library to do the calculation. So we have to represent the matrix, and here we use this embedded array, and essentially we use square brackets. So we have an outer square brackets, and every row is within square brackets. So here 5, 1, 0, 0. This is the first row. Then comma, open bracket. The next row is 3, 5, 0, 0. Blah blah. And then the next row is 1, 0, 1, 0. And then and then we need to represent the right hand side of the vector. And we do that with a similar kind of structure. B equals empire array, open brackets, then it's square brackets, 12, 24, 5, 5, like that. And then the actual routine to compute the matrix inverse is, to solve this matrix equation, is np.lineage.solve, matrix, comma, vector, a, comma, b, which we define at the top. And then this finds x, which is the solution vector. So if we run the code, so the code prints out the matrix, prints out the vector, and then it prints out the solution. So the next part is one way of solving simple linear programming problems with just two variables is to use the graphical method. And so we're given here, we have a linear programming problem, just some pure mathematics, no applications, with two variables, x1 and x2. And we have some constraints, x1 and x2. And we also have the constraint that x1 is greater than, and x1 and x2 is greater than 0. So let's look at the solutions. So we're trying to plot the these constraints. So essentially we convert these into straight lines. So x1 becomes the x, and y is x2. And we actually kind of, when we plot the things, we just plot these lines as equalities. So there's a kind of trick to do this here. So we used the NumPy variables before. This x1 np.linspace creates a vector between 0 and 6 with 100 equal space points. And then here so we need something to plot. So here we need to plot x2 equals, so you want to plot y as a function of x2 as a function of x1, If we rearrange x1 minus 2x2 equals minus 4, we get x2 equals 2 plus x1 divided by 2. And the trick is, because this thing is a vector, so when we run it we can print this out. This thing automatically converts, evaluates x2 for every element of the vector. So this is a sort of vector expression. So x1 is going to be a vector with 100 elements in it. And then x2 applies this formula. And then similarly, if you rearrange 2x plus 1 plus 3x2 is less than equals 13, rearrange in terms of x2 is 13 over 3 minus 2/3 times x1. And here it'll create 100 vectors. It'll take the values of at every point in the vector of the array x1 and create x2. And then once you've got that, you can plot it using the matplotlib library. And you add in the label, what the line is. You put in labels here for the x label is x1, the y label is x2. And also I specify the range here just to make the plot look nice, between 0 and 6. This one, so plot to x lim means x ranges on the plot from 0 to 6, y ranges from 0 to 6. In the y direction, added the title, and then down here, the plot.text puts feasibility region at position 1, 1 on the graph. And then the final thing to do is plot legend, creates the legend, and plot show plots the graph. Let's clean the console. Let's run. And we get a graph. So here's the text written out of 1, 1. To this problem. The range is between 0 and 6, which are these statements here. And if all these things, if you're uncertain about what a piece of code does, sometimes it just helps to print stuff out. So I told you x1 was an array of 100 elements, values between 0 and 6. So we can test this by just by printing x1. Okay, so it starts at 0 and then has little elements at 6. And then similarly we can print what x2 is. Okay, and that's also an array of 100 elements. And that's just a trick. Sometimes if you don't always know what if you're facing someone sent about what the Python's doing, it's very useful to actually print out what's being calculated. Okay, let's go on to problem 3. So, I mean, the motivation is creating sort of white noise to jam mobile phone signals. And essentially, your part of this to write code is to actually write out a random sequence of numbers, random either 1s or 0s. And I gave you a hint code to do this, and also asked you to do a simple check. So if you look at Q3 lab solution, so I'm going to generate 100 random numbers. So the key library again is NumPy. So down here we create, if you look online, how to create random numbers. So V is NP is random numbers, is 100 random numbers, an array, and these random numbers will be between 1 and 0, but they won't actually be 1 and 0, they'll be floating point numbers. And then I have another array here, binary digits, NP zeros, equal to the number of samples, so I'm going to take as 100, I can change that. This line here, I loop over all the elements. So I have 100 elements, and I loop over all the elements. And the trick is, if the random number is greater than 0.5, I say actually the binary digits is 1. And because all it's been raised to 0, This means if the random number is greater than 0.5, it'll be the binary digit set is to 1. And then also ask you to count the number of binary digits which are equal to 1. And then also have this count true, and this counts the number of times you get 1s. Okay, again, I print these things out. And then, so I count the number of times the binary digits equals 1. And then I compute the percentage, the number of digits 1 over the total number of digits generated, to 1 and 0, which is dim. And then I convert that into percentage. Okay, let's run this. Okay, you can see it's produced a whole bunch of 1s and 0s. And roughly the percentage of 1s is 55%. And this is just to check, a very kind of crude check of how well the random numbers is doing. If you look in the kind of books, there are much more sophisticated ways of checking the random numbers. But at the very least, you'd hope that that with the random numbers, it would produce sort of 50% 1s and 50% zeros. And obviously, this number should get more precise as the number random numbers is increased. So if we look at what V is, the vector, this is the random number. So this is what this array is, random numbers. So this is typically a typical uniform random number, which uses random numbers between 0 and 1, and they're floating point numbers. And then what happens is so this number here will be treated as 0 in the binary digits, and this number here will be treated as 1 because it's greater than a half. This one's be mapped to 1. It's greater than half. This one's 1. It's greater than half. This one's 1. It's greater than half. And then down here we have something less than half, and that's been mapped to 0. And that's how the problem's broken down. And it's really just an exercise in generating random numbers and also using the kind of if statement. Okay, so question 4 is a basic linear programming problem. So we're going to use SciPy optimized linprog, one of the kind of standard programs for solving linear programs with Python, given some constraints. All right, let's look at the solutions. So there's a couple of key ideas in this one. This is a commentary. So we're given constraints, and then we have to convert that into sort of matrix notation. This is what SciPy optimized linprog takes. The other library we use, pulp, actually takes inequalities in a kind of more clean notion. So we have to rewrite these inequalities as ax less than or equal to b, where b is a vector and a is the constraints. So we're going to use the kind of traditional square brackets type notation. So here's the objective function, 3x, 1, and this is coded as 3, 1 in a list structure. Here we're going to write this, the left-hand side of this as a matrix equation. But remember I told you the actual linear programming problem does the form ax less than b, and because this is x greater than a number, you have to reorganize it. So that's why here and we have a -1, 3, well, we have a 1 minus 3 here, and so you have to make sure rearrange some of the equations so it's in the form of ax less than or equal to b, where b is a vector, a is a matrix, and x is the unknowns. Similarly here, the equality is greater than, and so instead of 2, 3 here, we move this over to the right-hand side, the -6 over this hand, and we have -2, -3. This one is already an inequality, 2x plus x2, so that can be, doesn't need any rearranging. And similarly, this one here doesn't need any rearranging. So the right-hand side, because we had to flip this over to make it an inequality, make this less than. So you get a -3 goes to 3 here, 6 here, -6. And then here, because it's already in the form of inequality, you get 8. and then 16. And the actual code runs, so I mean the key thing here is rewriting the maths in terms of matrix equations, and then once you've done that you have to put in the objective function, the matrix, the right hand side, the b's, and then some issues about bounds, which don't really play around with this problem. And then you run it, and it finds the minimum for you. So the code, this code actually only finds the minimum. So in the second part, I can actually use the same problem with the maximum. In that case, you have to actually flip f, the objective function of 3.1, to find the maximum. You have to flip this to -1. So now we have f neg, so -3 -1, and then that's the only thing you change. And however, when you've actually done the solve the linear programming, because we flipped the sign here to convert a maximization into a minimization, you have to flip the value of the objective function at the solution. So we've got to remember this -1. Okay, so just to recap, so when you're trying to minimize, you just code up the expression. You have to make sure the inequality is the form ax less than b. And if you're finding the maximum, you have to flip the sign of the objective. And then when you solve it, you have to flip the sign of the value of the objective function of the solution, and that will give you the final answer. So let's do run. Okay, so in this case we have, so the minimization, we find minimum value at -9, -3, 0. And then when we maximize, find the maximum value of 12 at 4, 0. Okay, so now let's move on to question 5. So this is a Monte Carlo question. So you can estimate integrals by using random numbers. So we're kind of treating this as a probability density. So here it's the uniform probability density, and then f function s is the thing you're estimating. So you can estimate this thing by generating uniform random numbers between 0 and 1, which is Ri, and then summing over them to get an estimate of the integral. And then you can also do the standard deviation, which will give you an estimate of the error. And I ask you to do this for this function here, 50 cos 50x plus sine 20x, and then all of that squared. This is Q5. This is the program. So we're using math, we're using NumPy. So I've coded the integral as a function. Okay, and I've taken cos 50x plus math sine 20x, and I'll ask that to be squared. So the first part, you can actually do this. I mean, Monte Carlo doesn't only make sense for in many dimensions, in multiple integrals. For one dimension, it doesn't really make any sense, but you can. I mean, it's good for testing algorithms such as stratified sampling, which we didn't really investigate too much at the moment. So we can actually just use this routine here, which I imported from the SciPy integrate import quad, which does quadrature. He takes as a, so this is not a random number. It's not a Monte Carlo method. It's just a standard method like he did in the first year. So he takes an argument of the integrand, and then it integrates it between 0 and 1. That gives you a value. Then the Monte Carlo method actually uses these random numbers. So I generate 10,000 random numbers, 10,024. So this is what this statement here does. V is a NP array, and it's NP random.rand with n sample. So you get this, you get uniform numbers between 0 and 1, random numbers. Then this this piece is so then you could just loop through these random numbers and code this up as applying the function to each random number and then putting that in an array. I've done something a bit more fancy. So what this map does, it applies the function integrand to the vector v. So essentially, v's are random numbers, 10,024 random numbers, and then this fancy command applies map, applies the function to each element in the array v. This is what the list, and this is what the map does, and then it converts that into a list statement, into a list structure, and then you convert that into an np.array. So that gives you the function on the n sample numbers, and then once you have that, you can compute the mean, which is this expression here. You can compute the standard deviation and the error on the mean by computing the standard deviation and dividing by the square root the number of samples, and this gives you a Monte Carlo estimate. Okay, so let's run it. Okay, so the quadrature method, this quad method, integrates the number between 0 and 1 and gets a very accurate number. This is an estimate of the error, so it's very, very accurate. The Monte Carlo estimate gives an estimate of the integral, and it's not exactly the same as the kind of more the numerical method, but when you account for the errors, the numbers should be similar, and indeed they are. 965 compared to 0.978, and the error on that was 0.1. So the error is fairly big on that. And this is also a trick. I mean, if you use two different methods and the numbers are very different, then that's an indication that you've made a mistake somehow. But because statistically you can also estimate whether 0.9782 is close enough to this, and in this case the size error bar is fine.